Hey, everyone. Thank you so much for having me. It's really exciting to be here. I've never been to Malaga before, and it's been really nice seeing the city. Doug is a really hard act to follow, absolutely amazing, but I hope that you will enjoy this just as much. This is not going to be a talk that you take back to your company and go, we should use this. But I hope that it's one of those talks I hope will show you the potential of the web as a platform. Like, I don't know about you, but I feel a bit like the web isn't cool anymore. Everyone wants to build apps. And I mean, whatever, but I think the web is better. And there's a lot of really cool stuff that you can do with the APIs that are built into the browser. So this is one of those things. My name is Sophie. I don't have purple hair anymore, but I do still kind of look like that. So yeah, I'm the web engineering lead at Monzo Bank in the UK. I'm also a musician, and I conduct a choir. So yeah, I really love music, and there's a lot of music in this talk. I have a website at localghost.dev, or you can find me on Mastodon at sophie@social.lol. And that link in the corner there is like a little business card thing where you can find my Twitter and my Mastodon and email and stuff. And this is my virtual piano. I use the word piano, keyboard, synthesizer interchangeably. They're definitely not the same thing, but virtual piano was like a shorter name. But I'm going to tell you how I built it. I'm going to tell you about the musical theory that went into it. And I'm going to also show you a bit of the APIs that power it. So the web audio API and also the web MIDI API. But first, let's see what it does. So it plays scales. And it also plays chords. More scales. Different kinds of scales. It plays chords as well. Sounds quite rough. And you can click on it to play notes as well. So before I get started with the code bit, I'm actually going to start with some musical theory and a little bit of science, because the theory that I'm going to show you actually went into building the app, which I think is really cool. And I know you're thinking, this is a web conference, what are you doing? But it will all become clear, I hope. But we're going to start right at the beginning. Sound. Sound is made up of vibrations that travel as waves through the air. And the number of these vibrations in a set time period is what we call the frequency of the sound. And we measure frequency in hertz, which is 1 wave cycle per second. And when you think of a piano, when you press a key on a piano, that's actually making a hammer hit a string inside the piano. And these strings are tuned to vibrate at very specific frequencies. And in Western music, we have a set of tones that have very specific frequencies. And I'm using the kind of notation system from the UK and the US, at least. But we have 12 notes, each of which has a letter, A to G. And these notes are divided based on their frequency. And you have the 7 A to G, and then you have what we call accidentals in the middle, the black keys on the piano. And these aren't different enough from the ones either side, so they don't get their own letter, they get a symbol, and they're either sharp or flat, depending on where you're looking at. So they're the sharp of the one on the left, or the flat of the one on the right. And we're talking about notes as they are on a keyboard, so starting from C. An electronic keyboard has 61 notes, and it goes C all the way up. A full-size piano has 88 notes and starts from A. And the notes repeat in groups from lowest on the left to highest on the right. And these groups of repeating letters, we call them octaves. And on a keyboard with 61 keys, we have 5 octaves. On a full-size piano with 88 keys, we have 7¼ octaves. And I'm going to play you 2 notes, A in the 4th octave, or A4, and A in the 5th octave, A5. And it's a weird ability of our brain that we can hear these 2 notes and kind of tell they're the same note, they just sound different. And they are the same note, they're just pitched differently, so one's higher. And that's because each octave jump, the frequency doubles. So that first note I played you, A4, has a frequency of 440 hertz, and A5 has a frequency of 880 hertz. And that's true for all of the notes on the piano. Each octave up is double the frequency. Now, music tends to use only some notes, not all of them. So we have scales, which are like ordered sequences of notes, and they're like a set of tones that you can use to build music out of. Think of them a bit like a color palette that you can use to evoke different emotions. And when music uses the notes of a particular scale, we call that the key of the song. So if you have a song in the key of C, that means it uses notes from the C major scale. And this picture shows 2 octaves of the C major scale. There's musical notation, don't worry too much about that. But the notes on the piano that you see here are the notes in the C major scale. But the important thing here is that scales follow strict patterns. This is the G major scale. It has slightly different notes, so we've got an F sharp here instead of F. But the actual notes that make up the scale can be calculated using a pattern. So there's 2 important words here that they're very English. So you have a tone and a semitone. So a semitone, or a halftone, is the distance between one note and its nearest neighbor, either side. And a tone, or a whole tone, is 2 semitones. So the pattern to calculate any major scale is tone, tone, semitone, tone, 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 semitone. Every single major scale. So if I start on any note on the piano and go 2 notes, 2 notes, 1 note, 2 note, 2 note, 2 note, 1 note, I get the major scale for that note. And other scales have different patterns, but are fundamentally the same. And what do we love as programmers? We love patterns, right? Okay, enough musical theory. Let's get on to some code. I'm going to talk about the Web Audio API now. So this is a super cool API, and I don't have time to show you all of the things it does, but you can do things like you can play audio, you can mix it, pan it, put filters on it, you can analyze audio that's playing and make graphs and visualizations, a bit like Winamp, and you can also synthesize audio, and that's what I'm doing. So those sound waves that we looked at, well, synthesizers generate these waves electronically to make sound. So we're going to build a little synthesizer in the browser. So what do we need? We need an oscillator, which in real life is an electrical circuit that produces an alternating waveform that makes a sound. We need to know what kind of waveform we want to make, so the shape of the waveform will affect the sound that comes out. We need to know the frequencies that we want to play, so what are the frequencies on the piano? And finally, we need a user interface to be able to play the notes, so we need to build the actual piano keys. Well, to begin with, to initialize the audio API in the browser, we initialize what's called an audio context. And this is like a really big graph that contains a lot of audio modules linked together. And this exists on the window object in the big 4 browsers. It's got really good support. We only want one of these in our app. And then we can create an oscillator node. And we connect this to the audio context destination, which by default is the computer system output. But you can have different destinations depending on what you want to do with the sound that you're creating. But right now, nothing's happening. So we need a waveform. And so the shape of the waveform, as I said, determines the sound that comes out. And there are 4 really common waveforms built into the audio API that you can just define as a type on your oscillator. And a sine wave will make a very different sound to a square wave, for example. So let's have a listen. There's a sine wave, a square wave, a triangle wave, and a sawtooth wave. So I've gone with a triangle wave. And so I set the type of the oscillator to triangle, and I start it. And at this point, my app will be playing a fixed tone at 440 hertz. So what if we want to make different sounds? This is where we need to calculate the frequencies of different notes. But luckily, we can calculate them using a formula. Now, before I continue, A4, that I played you earlier, is a really important note. It's the A in the 4th octave of the piano, so it's kind of in the middle. But But it's also standardized as ISO 16. It's a standard orchestral tuning frequency. And this is because not only is it in the middle of the piano, but it's a really nice round number, 440 hertz. And the formula to calculate the frequency of the note is based on its position relative to another note on the piano. And so if we know another note's frequency already, we can use that to calculate it. And so it makes sense to use 440 as a constant to calculate the frequency. And this is that formula. So it's 440, the frequency of A4, multiplied by 2 to the power of n over 12, where n is the number of semitones between A4 and the note that we're looking for. So how many notes apart is it on the piano? For example, the note C5, C in the 5th octave, is the next C above A4 on the piano. So if you're looking at a piano, it's 3 notes above A4. So that would be 2 to the power of 3 over 12. So this is how I translated it to code. The function takes a letter and a number combination, which is the note and the octave. And the first thing I need to do is figure out how many notes apart A is from my note, as if there's only one octave on the piano, C through to B. And so I have a lookup table, hard-coded, of all the notes in the kind of semitone distance from A to my note. So if I'm looking up C, that's 9 notes below A in a single octave. Then I need to figure out how many notes there are between A4 and A in the octave that I'm looking for. So if I'm looking for C5, that's in the 5th octave. So I need to figure out how many notes there are between A4 and A5. So I subtract a 4 from my octave and multiply it by 12, which is the number of semitones in an octave. And this will give me how many notes apart A4 and A5 are. And finally, I add that to the distance in the same octave, and that gives me how many notes apart A4 and C5 are. Finally, I take the result of that and put it through the formula. A4 to the, multiplied by math.pow, 2, and then steps over 12. And that will give me the frequency. And then I can round it to 1 decimal place for convenience. So once we've got the frequency, it's simple to just set the frequency on the oscillator. So now we can make the oscillator play whatever note we want. And now we can build the piano. So I actually built this in React originally, and I had a whole section of this talk about how buggy it was. And it turned out it was my fault. It's not a buggy API, it's just that the way I'd implemented it in React just wasn't working. So I built it in vanilla JavaScript, which is much better, so make of that what you will. Each key is a button, and it's positioned with CSS grid. Each note has an ID, so I have an array of notes, of all the notes that I want to be able to play on this keyboard. And then each key on the piano has an ID corresponding to the index of that note in the array. And each key has event listeners for mouse down and mouse up. So we either play or stop the note when you click and release. And there's also a pedal, which means if you want to hold notes, then when that's enabled, we don't stop the note when you release the mouse button. And that's so that we can play multiple notes at once. So when it comes to actually playing the note, we create a new audio channel for each note press. So I'm not creating an oscillator, first of all, this time. I'm actually creating a gain node. And gain is, in real life, it controls the amount of voltage that is going through the system into the amplifier. And I've used this here to soften the sound a bit, because it can be quite harsh. So what this does is ramp the sound up and down again to make it sound a bit smoother. So we create the gain node, like we did the oscillator node before, connect it to the audio context, and then what we do is set value at time. We start at 0, and then we ramp it to 1 on 0.06 seconds, so it's really quick, but it just softens it. And if you're familiar with kind of musical terms, it's controlling the attack of the note. And then we initialize our oscillator, and we connect it to the gain node. So think of it like a chain of modules. Each one has to be connected to the last one. Again, we set the type of the wave and the frequency of the note that we want to play. And finally, we add an event listener to the ended event. So when the oscillator stops, we disconnect the gain node. And this means that things will get garbage collected at the end so that we don't have lots of nodes hanging around afterwards. So when we click a note, we initialize the audio. And we had to do this here rather than when we initialize the app, because you actually can't autoplay audio anymore. I'm sure many of you have memories of irritating pop-up adverts playing music, and that's exactly why. So you have to initialize the audio context in response to a user gesture, like a click. So once you click the note on the piano, we'll initialize the audio if it's not already initialized. Then we find the note that we're looking for that note that we've clicked. We initialize the audio channel and start the oscillator, and then the note plays. We store all of the channels in a global variable so that we can keep track of what's playing and stop things if necessary. And to stop a note, we do the opposite of what we did before. So we ramp down to 0 very quickly, and then we stop the oscillator. And you can pass in a time to the stop function, which means it will stop at a certain time. And when the oscillator is turned off, it disconnects itself. You actually can't start and stop oscillators. You have to use it. It's like a one-use thing. So when you start it, you stop it, and then it dies, and you have to create a new one. So every time I play a note, I overwrite the channel that I've stored for that note so that the old one gets garbage collected again. So to play scales automatically, remember those patterns that we can use to create scales? I've got a whole table of intervals for scales. And if you remember, the pattern for major scale was tone, tone, semitone, tone, 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 semitone. We can translate that to numbers, the number of notes between each note in the scale. That's 2, 2, 1, 2, 2, 2, 1. And we have 0, which represents the root note of the scale, the starting note. And so when I'm generating a scale, I have an octave of notes. And I iterate through the pattern, starting at 0. I have a cursor, a current position, that keeps track of where in the scale I am, and then and which note I'm on. And then I add each interval to the cursor to get the note at that position. And then get an array of notes which represent all my notes in the scale. And when I'm playing the scale, I only need one oscillator because I only want one note at a time. And while you can't stop and start oscillators, you can change the frequency. So I have timeouts per note, about half a second, so that it plays each one for half a second. I multiply that by the index of the note to stagger the timeouts. And as the timeout elapses, the oscillator frequency will change. And then I can store these timeouts, again, in a global variable so that if I want to stop everything, I can clear all the timeouts. For chords, the principle is very similar, but the patterns are different and there are fewer notes. So I've got my table of chord intervals as well. So for example, a major chord is like 1, 3, 5. So I'll get the oscillator this time. Well, this time I need more than one oscillator because I want more than one note at once. So I need an oscillator for every single note in the array. And so I create a new one for each note, and then I set them to stop playing after 2 seconds. So the chord just plays for 2 seconds. Cool, so what can I do? I can play notes with the mouse. I can play scales. I can play chords. Job done. But I decided to add a new feature. This is a MIDI controller. And what this is, it looks like a little musical instrument, but it actually doesn't make any music itself. It sends data when you press buttons. And these buttons tell MIDI, I guess, well, computers, what to do when you press the buttons, right? And so MIDI stands for Musical Instrument Digital Interface. It's a really, really old standard. So it's really well established. So I'm playing with fire here. I'm going to try and do a live demo. Ha-ha. Right. Cool. So I have my little controller. I'm going to try and play it like this, which is super awkward. Nice. Yes, I play all the hits. Cool. So What's actually happening here is that I've hooked the app up to the Web MIDI API. So this is, hang on a sec, yeah. So this is currently supported in Chrome, Edge, and Opera, not Firefox just yet, but I think that's coming soon. And when you press a note on the controller, it sends a message to the computer with information about what button was pressed. And the browser is listening for those messages, and the app knows what to do when those messages are received. So to talk to MIDI, the computer's kind of MIDI setup, first of all, you've got to check that navigator.request MIDI access exists, because it doesn't in Firefox yet. So you call navigator.request MIDI access, and then there's a callback that you can use once it either succeeds or fails. And this callback receives data, and that's data about the computer's MIDI setup. So it will have things like all of the inputs that connected to the computer. So if you have lots of different MIDI devices connected to your computer, then it will list all of those. It's also got information about outputs, so any MIDI outputs that are connected at the moment. I only care about the inputs for this one. So I call MIDI data.inputs.values to get an iterator of all of the inputs. And for this, all of these keys, and all of these keys, and all of these knobs are inputs. So all of them will send data when I press them or interact with them. So for each of these inputs, I'll add an event listener, which says when they send a MIDI message, then call handle MIDI message. And when I call handle MIDI message, they send us data, and this is what that data looks like. It's an array of 3 values, and the array contains the command, so which key did I press? Oh, no, sorry. Command is what did I do to the key? Did I press it? Did I release it? The second one is which key I pressed. And the third one is the velocity. How hard did I press the key? I don't care how hard I pressed the key for this, but that would be good if you wanted to make say, a keyboard that responds differently if you press it really hard or really softly. The 2 commands that we're looking for are 144, which means note on, and 128, which means note off. So when I press down on a key, it's 144. When I release it, it's 128. And this is a small section of a MIDI controller. So this kind of represents what you see here. And the numbers on these notes correspond to the numbers. So the default octaves for my MIDI controller is 3 and 4 on a piano. I can change it. But for this, I decided to hard code it to 3 and 4. So my keyboard, if you remember, each key in the keyboard on my app has an index from 0 to 24, because there are 25 keys. But here we're starting at 48, which is the C in the 3rd octave, according to the MIDI standard. So in order to calculate what note I need to play when I press a button on here, I need to subtract 48, which is a bit awkward. But if I wanted to change the octave, I'd have to work that out a bit differently. So here's how I do it. So I find the note ID on the piano on the app by subtracting 48 from the note number that I received. Then calculate the note name, and then I will switch based on the command that I received. So if it's 144, note on, then I play the sound, and 128, I stop, and stop playing the sound. So let's have one more demo for a good measure. I had to play this. This is, oh, no, wrong one. Yeah, I learned that especially for you. It's my first ever piano concert. You can find the app itself on virtualpiano.vercel.app. If you use it on mobile, I'm not responsible for what happens. And you can find the source code at github.com/Sophie Koonin/virtualpiano. It's all open source. Thank you very much. Get in touch, sophie.omg.lol. I'm happy to answer any questions you might have.